Cool. Wow. I will just. No, I actually I am from IIT Bombay, and he is faculty at IIT Kharagpur. So yeah, we hadn't had. I wasn't. I'm not in touch with him, but yeah, if some case arise, I can obviously talk to him. Cool. Hmm. Hmm. Okay. Cool. Okay. Perfect. Yeah, actually, we can discuss it here if there are some doubts. Okay, I shall start now. I'm just checking that there is a lot of interference. Pramod, can I mute you? Oh, okay. Okay, I'm just trying to mute him. Yes, okay. All right. I'm just checking my recording is working because I will be uploading this on YouTube. Okay, uh, so our course name is Advanced Dynamics, and I am Anshwan Mehta, and I am PMRF PhD scholar. I am currently in 4th year, and my research area is so I am in aerospace engineering, and my research area is a lot more interested in advanced dynamics because I work into aero servo elasticity. So actually, it is aero servo elasticity. So we have heard aeroelasticity because it is an interaction between the structures as well as aerodynamics, and my area is also servo. So kind of dynamics play a very important role in my research, and so so I will give you my contact number if some problem arises. So you can WhatsApp me if there are some issues or some questions which is regarding this or the course, and there is also portal where you can put the questions, so that you would be knowing because of the NPTEL. So apart from that, I am giving my own number so that if some problem arises and something is bothering in your mind regarding the subject, you can obviously ask me, or we can have a quick discussion about things. Okay, so I am a PMRF PhD scholar in IIT Bombay aerospace department. Okay, just write WhatsApp. Okay, so week 1 consisted of coordinate systems and relative motions. Okay, what is the code for? I think it's +91. Okay, I think this will work. Okay, now, so yes, so this course is little advanced than the dynamics. In dynamics, we used to cover what is kinematics, and then how we can convert everything into kinetics and find the forces. So similar thing we have to do here, but with a lot of complexity into the play. The complexity coming from the motion, how things are moving, because now we are talking about multi-body things. So actually this course is all about flexible multi-body dynamics, and it is having uh, if one link is there and some other links are also there which are affecting this link, so hence it becomes a very complex phenomena, because everything is moving with relative to each other. So for that we have to first set up a base, like a reference system. So first we have to know about the coordinate systems. So did you all go through the lectures, week 1 lectures? So week 1 consisted of coordinate system and relative motions. So just a quick question. We see that our Earth is here and it's rotating, and it is slightly tilted also. But right now, for our simplification, if we say that our Earth is moving in a perfect rotation, and we are not considering revolutions for now. Let's say we are in outer space somewhere where with so we can see the Earth just rotating. We are not considering that revolution thing, okay? Because now it depends on what frame we are talking about, like what is moving and what is at rest. So to give a clear idea, let's say I am in Mumbai, and if I wanted to see where the like how Mumbai is moving with respect to the space where I am right now, like let's say I am an alien, and I am just looking at Mumbai. So as you can see, Mumbai is in this line. Okay, so also the clouds are moving and everything is moving in this earth, and I am standing outside. Now for me, Mumbai is moving in, let's say, a circle, okay? Because this will eventually become a circle. Right now it's ellipse. So this is something like this ellipse. So Mumbai is moving as a circle. So this is one frame of reference. The another frame of reference is, let's say I have put a satellite such that it is just facing, like let's say India or the southern Asian countries, and now if I look from that perspective, I will see that Mumbai is at rest. Okay, so here Mumbai was moving in a circle, but now here it is at rest. So if we are given these two coordinates, so there are some changes and there are something which are same. For example, since we have neglected revolution altogether from both frames, so hence that is same, okay? But what is difference is now our satellite, instead of revolving around the earth or having a stationary point with respect to rotation, it is now stationary. So kind of we eliminated the rotation terms, okay? I will just give you a brief summary of what flexible multi-body systems are. Actually, this is my full aero servoelastic system, and it consists of a lot of subsystems. So in that, aerodynamic system is there. We are not going into that. Actually, that is very it is a part of advanced dynamics, but let's see how much can we cover. Majorly we will be doing this flexible multi-body dynamics system. So I will just take this circle which is of our interest and put it there in the notes. So it's of different color. So flexible multi-body dynamics, or we can say it as advanced dynamics, can be combination of these circles which have obviously the structural mechanics or structural dynamics, which is our just dynamics. So this is advanced dynamics. And structural dynamics is just our dynamics which we learn in our basic course. So it consists of inertia, stiffness and damping. So all those terms in M, K and C. Now with also help of rigid body kinematics or rigid body dynamics as well as contact mechanics, this complex structure we can convert into again this dynamic equations. So forming of those equation, it's part of this course. What is not part of this course is material or kind of making the system more non-linear into nature, which is obviously coming to more real stuff. When we talk about real stuff, they are non-linear. So as much as we can go into non-linearity domain, it's like we are making the system more real. So that we are not doing. So our area will be somewhat restricted to this thing, but you can connect like if you have this course in your arsenal, actually you can connect to all those things. Finally everything will become equations, and those equations you have to solve. So it's all math. So talking about maths, so there is a difference between maths and physics, and the difference is called abstraction. So we have mathematical So we have mathematical model and we have a physical model. So when we talk about physical model converting into mathematical model, there is something called abstraction. And here we try to use physics and try to model the system into mathematical equation. And it depends on what degree of analysis we wanted to do. So it's an analysis tool. So everything starts with making a reference system. So here we will talk about reference system first. So just like sphere is a coordinate system, similarly we can say that planar or like if we convert this whole earth into a map, so we have actually mapped the system. So talking about coordinate systems, so one coordinate system can be converted into another coordinate system using mapping. So before moving forward, do you have some doubts? Like if you have seen the weekly lecture, the first week lectures, So are there any doubt, because it's like starting advanced dynamics from just like if you don't have background in dynamics, there will be a little bit problem. But if you are basic course, then I think it is all right. So then also, do you have any issues? You can We can discuss it here before I discuss questions or the practice problems. Am I audible? Okay. Okay, cool. So, do you have some questions regarding our week 1 lecture, which was coordinate system as well as relative motion? Okay. So, what I will do, I will start with the questions then. So before that, all coordinate system have a notations. So if we have a reference frame, so all these coordinate system can be explained in reference frames. Notations are, so let's say we have a coordinate system such as n, and it is shown by 3 mutually independent vectors. Let's say we have another spherical coordinate system E, and it is given by unit vectors as this. Now if you wanted to let's say if you want to express some quantities, it can be displacement, forces, even acceleration, so any quantities, let's say x. Okay, so whatever is in this side above is like from respect to which, and this is to where it's like, so with respect to what, and now where we are finding it. Okay, and also this is like which point are we talking about. Just like in our earth example, this was our P, and let's say these two coordinate system are different. This is like E1 and this is like E2. So here if you wanted to let's say position of Mumbai with respect to E2, and now we wanted to say how it's moving with respect to the first frame, so we will write like this, and this P. So this will be our, instead of x we can write some like displacement d. So whatever is the like in what space, it's like changing the space now. In this space, what is the thing with respect to E2. So this is our notation. The problem will become complex if we won't use these notations, because in 3D what happens, it gets a lot confusing, and right now we are talking about 2D only, and we will for today we will be only looking at the 2D examples. But keep that in mind that notations are important. Now we'll use relationship between inertial and non-inertial frames. So as I pointed out previously, that in this case we don't know what is moving and what is stationary unless we talk about the reference frame first. So if we have fixed that, okay, this is our reference frame, let's say this satellite is here which is seeing this point P in this. Now we have fixed our reference, and now I call this as a non-inertial frame, because actually I am moving, the satellite is moving around the earth. But if we talk about stationary thing, like some alien just looking at the earth as a whole, now that is called inertial frame. But again, this inertial frame and non-inertial frame are again subjected to what reference we are taking. For now, we'll just talk about if something is moving. If the frame is moving, then it's called non-inertial frame, and if it's stationary, it's called inertial frame. It is very intuitive to find things into inertial frame, because let's say you are standing and you are stationary and you see something moving, so intuitively you get key what happens because you are stationary. But there are lot of complex dynamics into picture, where let's say this solar system only, you are in Jupiter, and you are on Earth which is moving. Also there is a Jupiter, and the eye in that Jupiter, that cyclone, that is also moving. Now it's something you wanted to observe there. Now astronomically it's very hard to find out, because there are a lot of different frames set up, and if you find everything respect to sun, then also there will be a lot of what you call movements which you have to take into account. So in that case, what is inertial, what is non-inertial, it becomes a little bit tough. But for that particular case, you can say that you are where you are, like looking at the telescope or observing the that eye of that Jupiter, you are at inertial frame. Non-inertial is that frame. So you have to go to successive frames, and then you can find that movement of that. So that we will learn today, like how to jump between the frames to inertial to non-inertial frame by these relationships. Cool. It's okay if you have not finished relative motion. I will just give you a total description of whatever is happening. So let's consider. So in that course, what sir taught was relative motion. So if we have different frames and they are moving respect to each other, then if we have defined what inertial frame is, what non-inertial frame is, then we can switch the frames. Like we can quantify the quantities of interest in other frames also, which is moving. Okay. So let's consider this S0 frame be inertial frame, like it is at rest. So the task generally is to convert everything into this inertial frame, and let S be a rotating frame. having constant angular frequency. So here constant is of importance. And let's define this omega naught. Now omega naught, we know that it's a constant angular frequency, but with respect to what? With respect to s naught, which is stationary, and it is omega of s. So there are two coordinate system or two frames, one is s naught, one is s, and omega naught s is that constant angular frequency. And it is with respect to frame s naught. Now let's say a q is any arbitrary vector. It can be anything. It can be it had to be a vector, but it can be let's say coordinates of something in one coordinate of a point in one frame, or it can be velocities of that point, or it can be acceleration also. So now what this relationship say? Let's say sometime it changed, and now we have to find the time rate of change of q in frame s naught, which is related to the time rate of change in s. So it's like if some quantity is changing, so how that change will be affected in both frames is given by this relationship. The change in q with respect to the stationary or the inertial frame is equal to the change in of that quantity q with respect to the moving frame plus omega into that q. So this is very important relationship, and I will say this is one and only relationship which we have to learn in order to solve all the questions of this coordinate change. Like if some relative velocities are there, we can, if you understand this whole formula, okay, it's very easy to find anything or like all the questions of this coordinate change wherever this rotation is happening. Even the translation as well as rotation both can be covered in this formula. What yes okay, qs naught is equal to qs plus cross. Yes yeah sure. Yes no, it's not about constant. Like for our course structure it's constant, but okay, let me more generalize it more. Yes okay, yeah it can change, but right now in formulation why I've put as constant is because in our question generally the omegas are constant. So I will give you a bigger picture. It's all about perspective where we are talking about. Now we have Lagrangian dynamics. as well as Eulerian dynamics, right? In Eulerian, we actually are fixing the frame and all the particles are moving like this. Okay, in Lagrangian dynamics, what we do, we track the particle, we actually sit on the particle. Okay, so if we look into this formulation, then obviously omega is not constant. Okay, right now why I have taken this omega is constant, because let's say this earth example, that omega is generally constant. Okay, I have taken as constant, but yeah, okay, this is not a generalized formula, this is just a relationship between these frames. If we have a rotating frame with constant angular frequency, then we can write this like this. Okay, yeah, obviously omega is a vector and q is also a vector, we can have a cross product, and we can have like this is a yes, obviously that formula you have written is correct one. Is q of let's say respect to s naught is equal to q of s plus this omega into q. Yeah, cool. So actually this is what I'm saying, like Lagrangian dynamics and Eulerian dynamics. This is Eulerian and this is Lagrangian. And what we will get to know afterwards are, if we consider forces, these are called pseudo forces. So to keep things simple, I have just said here ki it is constant, it's not generally like necessarily constant. Cool. Okay, there will be change in time, sorry. Okay, so now let's say if this S frame is a rotating frame with constant angular frequency, and let's say S naught is, yes, yeah, okay, what I generally do, yes, I got it. What I generally do is I take different frames in different omegas, like different frame for different omega, and try to treat as a kind of whatever I have to change. Like if one rotation is there in one direction, then I will take that different frame, and then upon everything I will convert into that, and then I will look at the another omega. Okay, so let's say we have omega ijk, omega I cap plus omega 1 I cap, omega 2 j cap plus omega 3 k cap, right? If we have these kind of thing, now what I will do, I will take one frame like this, another frame like this, and third frame like this. Like I have a I can make this choice, right? So in that way I can actually optimize of what way I am going into the dynamics. So everything is sorted in my mind, because everything is respect to one change only. If you take like all the complex, yeah, obviously if you have understood the whole problem and you have in depth of whatever is happening, so you can obviously go with directly with the vector notations. But what I generally do is I simplify the things and try to understand with my own perspective. So it depends on different perspective what I wanted to do. Okay, so yeah, that is also a way. You can use this omega as a vector, so it doesn't have to be a scalar quantity, it can be a vector. Okay, cool. Now what we will do is we will try to find velocities and acceleration with respect to the inertial frame. So we can use this relationship only, and we can say that v, which is velocity respect to s naught, can be written as r is our displacement, so this is our velocity of so this is our sv. So if in any moving frame we know the velocity in that moving frame, so we can find because what is that velocity in the stationary frame. Okay, now we can differentiate this and we can find acceleration. So this is our acceleration. So this is kind of change of velocity. So it's a compound function. Which can be simplified So here the key observation are these two expressions, one there and one there. It is a physical meaning, like if one coordinate is moving and if we wanted to see the quantities of interest with respect to the stationary coordinate system, then there are inclusion of these two expressions, and these are form of pseudo force, like the additional forces which it will experience in presence of the moving coordinate system. Everything clear up to this point? Oh, good. So I will just solve this very simple question. there is a turntable and there is a and on that. And is walking, I don't know if it's correct, but it's walking along a radius of the turntable at a constant velocity. V naught. Now this is relative to the turntable. This is important, which is related to the turntable. Now you will get to know the benefit of this notation. Like if you learn, it's a like the learning curve is very steep, because actually finding everything into the term of these frames, it takes little bit of time, because to visualize what is moving with respect to what, and how we can find, like what we have to find, that is also sometimes the question. So now let me draw this figure. So let's say this is our turntable. So we have this turntable, and let's say our ant is somewhere here. Let's denote it by 0.1. So this is our 0.1, and now it is going along the radius. So let's say it is going to 0.2. This is our 0.2. This ant is going from 0.1 to 0.2 with constant velocity v0. And this table is also rotating with the constant velocity omega naught. One more thing, one more quantity of interest, it's center of the circle. Let's say this is our center of the circle. Now we have to first define the reference coordinate system. So 1 I am taking as the center of this table. So if you look at from that perspective, everything is stationary and the disk is moving as well as the ant is moving on that. Okay. Another frame of reference can be fixed frame of reference, which we can treat as some place outside. is our fixed frame of reference. And this ant is moving from point 1 to 2. So my question at this point, like that ant, it wanted to go to that point too, like along the radius, but will it be able to go there? Like, will it be able to reach at point 2 if the table is rotating? Yes, yes, Rafael. Yes, yes. Mm-hmm. So let's say we are that ant, okay? Like let's say I am that ant, and there's a huge platform and it's rotating. Now I wanted to go there. Like I have a friend at point 2 at that point, and I started moving towards him. Okay. Now will I experience some force or not? Like that is the issue. Yeah, yeah. Hmm. Hmm. Okay. Hmm. Exactly, Coriolis is force. So these terms are actually the. Hmm. Hmm. Cool. Hmm. Great. And the strange thing is, we haven't talked about the masses, like the inertia terms. Like then also we are talking about the forces. So these forces, yeah. So I made it tricky because to like when we have confusion, then only we will have clarity, right? So so like if I have a friend there and I wanted to reach to him, and because of the rotation, I will experience some force. But what is that force coming from? Like because of my mass, it can be. But what is that force like? Because right now we are not talking about the kinetics. We are only talking about kinematics and like how the velocities are changing. So these forces, which we call as pseudo forces, which we experience because of the change of the coordinates. Okay, so these are the forces which everything experiences if it's moving, like if it's observed in the moving frame. Because if that frame is moving, because of that only we experience some forces, which obviously called Coriolis force. So these are the forces which is the cause of the weather, and which is also cause of sniper shooting. We will have one more example like that, in which like a sniper is shooting, and because of the earth movement, the kind of the bullet curves. Okay, so something like that also we will have as example. So yeah, great. You finally you got this point. Like they there will be some forces. Okay, like so it wanted to go to the point 2, but because of some reason it cannot, because it's trying but if we haven't taken that movement into account, it cannot reach to point 2. But if already he has taken that account, like he is accustomed to it, let's say he is accustomed to it, is accustomed to that movement with which we are actually on earth, because we don't feel the earth rotation, right? Because we are accustomed to it, so hence we don't feel, like we said, that we are stationary, but actually we are not. So hence, what is stationary, what is moving, it's like, it's a little bit relative term. Again, we are talking about relative motion. So cool. uh, yeah, sorry. Yeah, so along a radius. Hmm. So along the radius of the turntable, yeah. So yeah, this is very important statement. So we have to find, what we have to find is acceleration of this ant related to the fixed reference system. So here we have defined that fixed reference system is 0, x and y. Now there are different methods. One is by which we can say that point C is at, so we can make one diagram. Let me make that diagram. This is center of this circle, and let's say this is point 1, this is point 2, this is radius, this is distance from center to the initial point of the ant, and this is delta r, which is change in radius, in position. And now at some point it will be moving from point 1, the table will be moving from point 1 to 2. Let us denote it by 2 dash. Okay, so 1 will also change from 1 to 1 dash, now this this is V0, and in this direction, because of this movement, it will have omega naught r. But at point 2 dash, what will be the circumstances? Again, V0, it will be moving with V0, but here it will be tangential to this, and this will be omega naught r plus delta r. So this is one way where I am going to this acceleration. So looking at the only radial change of velocity, how we define the angles. So we have V naught here in this direction. We have to draw other set of so these are the angles. So V radial will come out to be V naught minus omega naught square R delta t minus omega naught square V naught delta t square minus V naught. Now simplifying, equal to 0, we will have our radial acceleration as limit delta t tending to 0 v radial by delta t minus omega naught r. Okay, and this is called our centripetal acceleration. Now similarly we can find out tangential also. We'll just write down the final term. Yes. 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 Oh, I think there will be delta t. Sorry, again, I couldn't pay attention. Sorry, I was correcting my own. Yes. Okay. Okay. Delta t, yes. Sin x is equal to x when x is small, right? Because delta t is tending to 0. Okay. omega naught this right, this should be 0, right? This one, yes, this sign, yeah. Yeah, we actually substituted. Oh, okay. So you are telling about this thing, right? Delta t square. Okay, okay, okay. Let me check. V naught is coming from this. At which point? Up to this, everything is correct. Okay. Oh, okay, got it. So you're saying that if we have to put like this, then it should be x, not 0, right? Oh, okay, okay, okay. But eventually it will come to be same as this. Yeah, yeah, okay. Yeah, I can make changes. Okay. In final document, I will make changes. Okay. Okay, so similarly like this we can go for v tangential, delta v tangential, and we can write final expression of delta t. So this is the hard way which I am going. Now just imagine if this method I use, let's say in system of many ants, okay, upon which are moving with some random thing. Now if we go while solving like this, it will take a huge lot of time as well as effort. So hence these formulas help in that way. So yes, okay, like this, that formula, okay. Yes, yes. uh, but hence I have taken it constant. Okay. I just wanted to complete the picture. Okay, so it's like, yeah, obviously there are generalization of everything, but the thing is we should look at the perspective what we are getting taught. Okay, because taking everything into account, it will be like we cannot analyze this thing, like go into detail of it. Okay. Yeah. Yes, yes, yes. So this is called acceleration. So this question was just to give the feel of what the subject is all about right now, like the first part of this subject. First is called acceleration, and second is centripetal. Yeah, there will be one more term where omega dot terms will be there, and yeah, then it will become more kind of complex. So right now just we are starting up, and when we will come to the 3D problem, then we will use these formulas only, just to give the feel that if omegas are constant, just like our solar system, because in our solar system also mostly omegas are constant. If you don't take about minor it won't be minor effect. The scale is macroscopic, but if we compare like the small undulations with the constant thing. So it's like, moreover, it's the constant phenomena. So let's see if we can do that thing where we have one planet somewhere, another planet somewhere, and we are kind of tracking and finding the expression out of it. It will be an interesting problem. That's it. Okay. So this is one way to go. Another way of doing method 2. Yes, 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 Rafael. Yeah. Okay. Okay. Yeah. Yeah. So this is one problem. I actually wanted to go into 3D problems. Okay. Yeah, I am coming slowly to that, because actually those problems are meant to solve by you all only, because if I give the solution before the time period is over, then it will be a problem for me. But after 9, like for example, this first week assignment is like, the time limit is till 9th. Okay, so I am slowly coming to that thing. But after 9, I will obviously give you a solution, like how the questions are being solved. But to give you a base of the thing, to generalize things such as these questions, uh, so all these questions can be taken care by this formula. So today's actually is just going into it. Maybe next week onwards I will be more organized into this thing, like uh, observing the questions and then making something related to that, so that you are easily able to solve the questions. Today is all about feel, to take the feel of this subject. Let's see, because next class will be on, I think, 8th, right? It's in 8th. 7th. Okay. I actually, you can solve those questions if you watch the videos. Okay, this is for extra feel only, and if you have, obviously, yes, yeah, he okay, yeah, I will surely give a lot of questions and explain those questions. But my way of doing is like in an organized way, in such a way that I try to solve each question, like all the question, by one formula only. So I'm making that one formula, and how to utilize that formula, so that all these type of questions are solved. Okay, so change of coordinate, for example, will can be solved using this change of the coordinate system. Now about the other problems where moreover the kinetics into the play, so we will slowly come to all those subjects. Okay, because throwing everything at once, it will be very problem for me also and you also. I cannot explain a lot of things. So let's do it part wise. Now today is just about coordinate system and where is the subject, yes. So, and relative motions. Okay, no, it's not okay. So because if we look at the course structure, you will see that finally the kinetics will come into the picture, and then the how to formulate those problems, because we cannot do this just by the Newtonian framework, like just for each particle we cannot do like this. So we have to come to energy methods. So that is also the aim of this course, like that, because that is more scientific into nature. And also we can uh, bifurcate the problem into what analysis is, like what we wanted to analyze generally. And obviously this is the chart. So how generally I do these classes is, I have a intuitive way of solving these questions. Actually, I admire comics a lot, and in that comics, Batman is my favorite character. So what I do, I convert all these questions into Batman problem, like how Batman is thinking about things, and it's a non-linear dynamics problem, and something Joker is making a chaos of it, so something like that. And finally what I do is, I try to put everything into that frame. Let me show you some of my old lecture notes. You will find it fascinating, I think, maybe. So these are kind of my nonlinear dynamics notes, and I have just kind of made a comics out of it. So I wanted to try with this subject also, but eventually I don't have time for it. So this time I'm just solving questions and giving the feel or why we are going into this subject and how we can visualize things. Okay, moreover, I'm concentrate moreover on that, because applying the formula is easy, but how to utilize this formula by visualizing it, at what frame should we take. So this is the main task which I wanted to take care of. So right now we are in 2D problems. So there was one more problem which I have. I can put it on the notes. Okay, whatever I'm doing here, it's okay, but similar problem in the higher level, I will put in the notes. So if you wanted to practice more, you can use those questions. Okay, eventually my aim is to let you understand all whatever is happening. From next class I will delve into more about 3D problems. Alright, so 3D problems, I will make them interesting using some of my aerospace applications. So that let's say there is a Canadarm or something in which a space shuttle is there, and from there arm just extend out, and it has a end effector, and it is moving in some way. Now you are in control and you are trying to move it in some way, so you have to put some numbers to the system. So those kind of problem. Let's see. I think it will eventually we will all will catch up to each other. So yeah, but I always take this time. If you have any problem, you can just ask me right away. We will try to discuss it, like where the things are, how can we understand it, because it might be because it's an advanced subject, it might be I would be not knowing things just like this. For example, maybe I have made some mistake here. Let's see. I will just check it once and then put in the notes correctly. Rafael, any other issue? Okay, cool. Okay, so moving on to the second. So this is the first method by which we can find this. Second method is more over the formula based. So first we have to fix the reference frames, which we are already fixed. So this is the stepwise algorithm. First you have to put the references, like what the reference frames are, try to denote them into the notation. For example, here S0 is OXY, and it is having I and J. Since it's 2D problem, we don't have to take care of K, or let's say K also, because the rotation is involved here. Now H is our rotating frame. Also angular velocity, its value is given omega naught k. So here k can be used. Now if we wanted to find of acceleration with respect to the stationary frame, we can use it, do it like this. I can copy paste from there also. Okay, we know that with respect to the frame, moving frame, we know that the ant is moving in the constant velocity, so this becomes 0. Now the solution directly comes as 2 omega naught v naught I cap minus omega naught r j cap. So see, this is like more scientific into things, because once we have defined one direction, now other directions will be found accordingly. But previously we have to find, okay, in this direction it is going, now what should we do in the next direction. So it is more intuitive in nature, but this is more scientific into nature. So this is the first step to find the reference frame. Second step is to write what is known quantities, and third step is to apply formula. So just 3 steps, and surprisingly you will see that all these formulas are kind of all these problems can be solved using these formulas. I also provide, hello, yes, okay. Oh, okay, where at this point? Yes. Okay, here is the problem. So if we look at the ant, what forces, not forces, what velocities it is, like, because what I have mentioned here is this constant velocity relative to the turntable. So this is like v naught is respect to s. So this is given, okay, and this is constant, so which I have applied here. So you see, like this is fixed, this thing is fixed, yes. No, this like okay, I got the, so yours it's like what is moving and what is at rest. So right now we are making this as rest, like nothing. We can put the whole thing here also, okay, at here. But the point is, we have to think about this as a stationary thing, like it's all about like that earth problem, okay. In this earth, if we are, oh yeah. So yes. So if no, ij is not changing its direction with respect to stationary. That's what the no, acceleration is changing its direction with respect to these quantities. These quantities, these like no, actually this is not constant. This r is not constant. This r is moving, yeah. So this is obviously constant. This is called, this is acceleration. So this is let's say, because yes, okay, yes, please, first you tell what you mean. ijk in rotating. Oh, okay, got it, what the problem is now. Yeah, okay, we can do that, this extra step. So let's say sorry, this is 1, that also, okay, yeah, that also we can do. So let's say this is I1 J1 K1, and this is I2 J2 and K2, and we have a coordination, we have a mapping matrix from this to that, right? Okay, so first of all, k1 is equal to k2, as you will see that only everything is moving, but k are all vertically up. Okay, so this is what is making the difference. So here k, so yes, why I am saying that, because I2 and J2, yeah, we can take those, but eventually we have to convert this I2 and J2 in form of I1, J1 and K1, because I1, J1, K1 is a stationary thing. Like that is the thing which we have defined as it is stationary. This is at rest. Other things are moving, like I2, J2 and K2 are moving. In this case, K2 is not moving. I2 and J2 are moving because of the rotation, but I1, J1 are stationary. Okay, so what we are doing, like this formula is all about relationship between the inertial and non-inertial frame. So if we have inertial frame as rest, and if we have some non-inertial frame moving around anywhere, okay, so we can quantify that a non-inertial frame in this inertial frame. So this inertial frame we have defined by default that it is stationary, like I, J, K, those are not moving. Obviously the I, J, K of the non-inertial frame are moving, but we have a mapping matrix into account, which is like your cosine, that matrix can be there, the rotation matrix. But to make things simple, I have converted into these formulas. Okay, yeah, that is also one way we can go, but the thing which become more problem is this velocities. Now when this rotate, this change in respect to time, if you find out, then it kind of haunt us, because I will show you a problem like which currently I am facing myself only. Okay, sorry. Hmm. Okay, we are going like that. Okay. Okay, so let me, we have to make little changes here. I'm just doing that. No, there is no disagreement. I agree with you. So S not. So not S. So S. This can be written as, now in term of so in which direction it is going, I or J. So I can make one more thing, one more uh, coordinate system, the inertial coordinate system. Let's say on the body centered. Okay, like at the end, and where the and is, I can make one more coordinate system there. Okay, yeah, I'm doing that. Yeah, that is not an issue. It can be done. So let's say this is I1. Oh, sorry, this is I1, right? And this is I2. This is J2. This is J1. This is what you are saying, right? And now we have to define everything. So V0 is defined in J2. V0. Yeah, it can be also done. Okay, so but this I cannot show pictorially, but this is at the center. Here is the problem. Now see. Yeah, got it. See, if we are taking reference at here or other point, it doesn't matter right now in this question. Once again. Okay. So if we take here the initial frame, or here or here or here, okay, if we say that this is fixed, it doesn't matter like where we are taking this inertial frame. It's like grounding. We're grounding the system. Okay. So now the point being, what we are taking here, okay, because this J2, why I am taking J2 at the and I will say and, because it gives more intuitive into body center things as well as the inertial things. Like if we have a inertial frame and we have a body center. Like you are traveling on a train, and now you are in that train, you are being the observer now. Okay, so you will see everything moving. Okay, so hence I took this J2 at the end only. Okay, it give more intuitive sense, but yeah, obviously you can take it into center, you can make it now, because J2 it won't change, V2 will be in J2 direction only. Okay, one more thing can be, yeah, only those two quantities will be changing. Now applying this formula, now we have to take care of this directions only, because it is all cross product, it's all cross product, and this cross product can be written in term of this J1 J2 K1 K2, because we have a mapping matrix here. Okay, so I will give you a similar situation what I am facing right now. Like I have a airfoil, like I'm in aerospace, so we have a airfoil and we kind of map this airfoil into a circle. Okay, and it's called Joukowsky transformation. So it's similar to the mapping only. Now that airfoil is actually moving in inertial frame, so it's moving somewhat like this. Okay, like in some way, but what we have to do is we have to pin down that uh, whole airfoil into this, and we will say that whole world is moving now around it, so it's a flow past some bluff body or some streamlined body, depending on which study we are doing. Now then we have to convert this whole airfoil into a circle, so that we can apply some boundary conditions or those things. Okay, so we have to change the coordinates. All right, so it is all depending on that coordinate transformation, how we do. So this J1 J2 and I1 I2 and K1 K2, they also have a similar transformation matrix. Okay, which we can easily get by just observing the frames. Okay, for example, if we take this as I1, this is J1, this I2, this is J2. Now we can easily define how this J1 J2 are changing in unit time, and we can convert into a transformation matrix. That is also one way to go. Okay, so I'm just streamlining the process. So I'm providing everything into coordinate system, because whatever you are saying will be taken care of this cross products. All right, you can try it. We will have more feel of it when we will be going into. Yes, hello. Yeah, I'm going to. Okay, next problem, I promise it will be I1 J1 K1, I2 J2. Yeah, I got it. Okay. Okay, can you send me the solution of it? Yeah, obviously you can send me the solution of it. Okay, let's have a, yeah, cool. Cool. Okay. So no, next question is all about like we have a turntable. Just let me share this next problem. Okay, so our next, this is the first question which we have solved. Okay, now just to make little bit coming out of the studies. Okay, So yeah, now this is a problem where lot of rotations are there. Okay, so you will have ample time of I, J, K. So the S naught is there, which is fixed. Purple frame, I will say. Purple frame is where the purple frame. Don't have purple frame. I think that, okay. See this here, the arrows are there. So these are purple frame, I, J, K, and it is like fixed. Okay, everything is moving respect to this. Now we have S1, which is rotating invisible frame on top of this S naught, and it is like platform D, the blue circle, the blue platform that is there, like light blue. And now we have a rotating pink, which is like 600 offset of it, of the center. That is the third frame. So we have, now I have denoted this K, all K's are same, all K's are same because everything is pointed vertically up, so it's a planar problem. But IJK and IJK are different. So now if you convert all those things into this form, like the known quantities and unknown quantities, we can finally find each and every point. This is what you are mentioning, this I1 and J1 everywhere. Rafael? Cool. So can you see this cross product? So when we do this cross product, we actually, those terms like J2 terms and I2 terms, they actually cancel out in that question. Okay, and finally what is left is all into this fixed frame only. Like, okay, that is the actually the aim of this type of question. Like, we wanted to convert everything into analytical expression into this fixed frame. What we are aiming, okay, so this I will provide in the notes. You can check those expressions. There will be minor problems, but not. This RA, these are the velocities, I think. This one, this expression. Oh, here. Okay. Where? Oh, this one. Okay. Yes. So this is our correlative right? Can you imagine this V naught? This V naught is actually the constant velocity. Okay. Yes, and omega naught is also scalar. So this thing in I direction, like at this point, if I will say, the I direction is this thing, right? So this is actually that this thing will be experiencing in this direction. Okay, and there will be a coming like centripetal force, okay, which will be throwing inside. So it's like centripetal force. Centrifugal throws you outside, centripetal kind of throws you inside. So yeah, so everything matches. Yeah. Okay. We are talking about dt here. Okay, yeah, obviously 2 dt. Okay. Okay, cool. Yes, I also know that. Like, why? Because at that time the frame has been changed. Okay, and actually what I'm trying to tell you, that the aim of these studies are to find everything in form of analytical expression. For example, let's say this t v naught is not constant; it's changing with time. Okay, it's a vt. Like, if not, I'm saying that if in some problem it is changing with time, right? But by kinematics we can find those expressions. Okay, just by the virtue of kinematics we can find this expression, the correlative expression. Yeah, cool. Yeah. So this is okay. I think I should write instant somewhere, right? We have to calculate. Oh, cool. Nothing to worry about. Hmm. Cool. Now we have clarity, right? So for an instant, this thing is happening. Cool. Okay, I think in most of the question I have written the instance. Yeah, that I can make changes. This is cool. Like, in an instant I have to write everywhere. In an instant, what is happening, and we are only considering that. Okay, in all the questions I will just in an instant. So this is also a similar problem in which I have just, the complexity is more because now, yeah, so everything is respect to this, the controller, and this end effector we have to move. Now what will be the acceleration, and what is the motion seen by that who is sitting inside. So that can be done. So we have two rotations here and one translation also. So this is a nice problem to check out. So these are all planar problem. Yeah, it's all for instant. I admit that. Hmm. Well, wow. Yes, yes. Yeah. I think from next time you should only take the class, and I will be like, okay, you're doing very well. Yeah. So this is the, we can come to the benefit of this method. Yeah, that's the one more thing. Let me just put one more add page. Yeah. Yeah, we actually we can code this. Yeah, I had tried. See, two reasons why this. By the way, that formula is called transport theorem. Okay, if you want to check it out. So transport theorem is generally about moving frames. Now, why transport theorem is better than, I will say, manual finding of the kinematics? Okay, one way is obviously it gives the direction and the magnitude, and it's a scientific way. Like, everything is set. Like, if you have set the problem beautifully, you can get each and every part of it. Now, what is second is, it goes well in hand with surrounding methods like Lagrangian mechanics. because what happens in Lagrangian mechanics is we track that particle, okay, and if that particle itself is moving, like in my airfoil problem, if that airplane itself is moving, now it will experience some forces. So what does this transport theorem do? It converts everything into that stationary frame, okay. So I don't have to take care of, oh, from this also the force will come, that also the force will come. So it goes very well with the Lagrangian mechanics, okay, and it's a scientific way. So hence actually we can code it. So we can use not only MATLAB, we can use a lot of other softwares also, and we can get to this multi-body dynamics, okay. We can control it, we can have a hands-on approach, and everything will be in your control. It like, if something is missing, you can have a methodological way to get into that. So this subject is all about that, by the way. So let's see how much we can gain from this subject. Any other issue? Right. Okay, yeah, so I have to change here all the instant and an instant and an instant is happening. Okay, if you will see in this method in which we try to track the dt of it, like in which direction it should go, and like putting the differential equation into the play, like for the small change how it will change. This is also way to go via defining the governing equation, okay. So it is moreover toward the making the FBD of things, the free body diagrams, and then creating the whole picture, okay. But as compared to this method with the right now our method is transport, using the transport theorem, we can easily find out what is moving respect to what. Just the thing is, the intuition should come, like what will be in rest and what should be in moving, okay, and what the relation in between those system are. Let's say we have what I was talking about is, we actually did this experiment in my subject. In that subject I gave an assignment, and that assignment was the same one which Jupiter red eye is there, and you are an astronomer in some place in given latitude and longitude, and you have to find the analytical expression of that eye of a Jupiter, analytical expression with all the movement into the account, whatever you can take. So the assignment was divided into, like, if you have done all the movement, explain them, not given the analytical, otherwise it would be a very huge project, but at least give the feeling of it, okay. Then it would be like, you will give you the full marks. But many of them couldn't do a simple transformation from Earth to Moon, okay. From there I had given this assignment from Jupiter, like Earth can be put as reference to Moon, but Jupiter cannot be put as reference directly to the Earth. So we had to resort to Sun first. So, and that too, now Sun is also moving, by the way, in a whole dynamic. So the point being, like, what is at rest? So if you treat Sun as rest, then yeah, you are able to solve the problem. Explaining that we are assuming Sun is at rest. But if you take this account that only Earth is moving and there is another orbit where Jupiter is moving, now the problem will be like, you don't have a intermediate reference frame, okay. So why I wanted to put this intermediate reference frame is because it gives more feeling to it, like how the question should be solved, and any complex questions can be broken down into parts, and a direction can be found, and just that those directions, and you have to convert into mappings, and you can code it into any software, and you will finally get the expression you wanted. Just that you have to take this abstraction. What I was talking about at first was, you have a physical model and you are converting into an mathematical model. So a kind of abstraction is needed, So this depends on what degree of detail you want. Like I can say that the cyclone is also moving, okay, in some specific pattern, but if do I wanted to take that into account, or just I wanted to observe that where that red dot will be at an instant. Okay, here also come the instant. So this gives the feeling of, if coordinate is changed, then what will be the forces affecting that. Okay, so the first part, which is coordinate system and relative motion, it is one of the complexity which we face when we go into advanced dynamics. Another is, if you will see in this figure, another is due to material. What we think is our system is we say it's a linear system, like everything is linear, the friction it also act as a linear cx double dot, but that is not correct picture. Like this mx double dot plus cx dot plus kx is equal to ft. This is what we have learned, how to find the responses of it, of a linear system. But actually this m can be like this, c can be like this, k can be like this, and upon that it can be autonomous also. So we have lot of different, and finding the solution of it, it is another task. So before going to solution, first formulation of the governing equation. How will you formulate it? Will you use the Newtonian approach, or will you use some Lagrangian approach, or some other thing which you will be learning in further in this course? That is there. And finally, why I am putting so many rotation into pictures, because finally you have to understand what how this gyroscopic motion are governed and how the gyroscope work. And also, yeah, so my final aim is to get to this analytical dynamics, where everything it can be put into equations, and now it's all about solving those equations. And yeah, next thing which is kind of introducing a complexity is constraint. Now constraint is something which we take very lightly. It's like, okay, this is constraint to that, but actually if you look into analytical dynamics, you are making a mathematical model out of it. Now you have to provide what constraints are, you have to provide what degree of freedoms are. How will you know that degree of freedom are independent to each other if something is not affecting the other effect? So for that you have to use something called Lagrangian multipliers, language multipliers. So you have to find out what quantities are dependent onto each other, because upon seeing a system you cannot judge, okay, this will be dependent on that, okay, because everything is khichdi here. If you mean what the word khichdi means, is like everything is put all together and now it's just cooked. Okay, so it's something like that here, and we have to find a specific way to enter into it, and then finally we can understand every bit of information what that physical model had to present. Okay, do you have some questions or something to discuss? We have 10 minutes to go. Yes, sir. Okay, cool. Yeah, yeah, this is the second time you're mentioning. Okay. Okay, cool. Yeah, actually, see, eventually it will come to these notes, okay? And if you have any doubt, you can actually message me, or you can email me also. I will give you my email ID, so you can actually email me. So it won't be like I will be pitch perfect into things. I will also need time to understand what actually the problem is, okay? So I will give my email ID also. That will be much better if you. Oh, cool. This is my email ID. Okay. Oh, okay. Okay. Last time. Okay, great. It's okay. So you can ask me questions if you have any doubt in particular in any case, okay? I will try to make it more organized into the setting that eventually you can solve as much questions you can, okay? But that's what I'm saying, like it's a learning curve is very steep, because uh, I have to put lot of things into picture, because it is from, if somebody would have not done the dynamic course, it's very hard for them, okay? But if somebody have done, then also there are a lot of bit of pieces which is extra into nature, all right? Because the thing comes, because as a mechanical engineer or as a thing, why we are into this subject is because we can visualize things, okay? So what I do, I actually try to do is visualize the whole scenario into your mind, so that you only can give you the solution or the intuition to find the solution, okay? My point is, so you can solve the questions in very easy way. You look at the problem and don't say it's like it's very tough problem. You just say, okay, this, it can be done that way. Now it's dependent on your effort. If you wanted to do that, solve it, okay? But you should know how you will going to solve this problem, okay? Hence I am right now this subject is all about abstraction only, okay? Why I am stressing on this thing is because all the physical or physical thing, like, as we go advanced, it's like we are going more toward the nature or more toward the reality. And as the reality is stuck, it's stuck in a lot of different ways. Each topic are research topics, okay? Each topic, if you go into detail, are research topics. um, Even if you go into, I will say, uh, constraints, still the research is being going on to the analytical part of it, okay? If you go into application of it, so Lagrangian mechanics are used throughout world in lot of ways. So we would have heard about interplanetary motions and those things that were also given into this format only, okay? So I think we will gain a lot of info with this subject and lot of insight, because that is what needed here. So any particular question you are very worried about, Rafael? Yeah, yeah. I actually thought 4 to 5 times before taking this subject. Then eventually I said, what worse it can go. I have understanding between all these subjects, because I had experience. I also had experience with all these topics in some way or the another. So that's why I was keen to teach this subject, so that I have experience of teaching whenever I will go outside or somewhere else. So it will be fun doing this. Okay. Cool. Thank you. Mm-hmm. Okay, so vibration of structure is moreover down to earth with this uh, subject. Like this is more toward the sky up above subject. So vibration of structure maybe is the course which you should concentrate more, because it will give you the feel of this equation mx double dot. Okay, so I wrote that this equation. Okay. Yes. Okay. Related method. Yes. Finding the solution of this part, right? Okay. Yeah. Eventually, we have to reach the Hamilton principle. Yes. Mm. Cool. Okay, so to add to that point, I will say that keep everything in a black box. Okay, like for example, a constraint. When you hear this constraint, just put it into some black box. Okay, eventually, slowly, like classes like this or in a search course, you will get to open those boxes and you will find out there are more black boxes inside. Okay, so we will keep on finding up to what depth we can go in this course. Okay, so yeah, so because that's why how I did, and actually uh, teaching a multidisciplinary course is really tough. And there are a lot of different backgrounds and a lot of different issues. So we have to go from base to I don't know where in some research area, but yeah, this is how the things are. Let's see. Okay. Yes, it gives a kick. Yeah. Exactly. I also feel the same thing. So I also in the learning phase. Like, for example, this instant thing never hit on me. But you said then also only got, oh wow, yeah, it's for an instance. Yeah, right, really, he's whatever you are saying, you're correct, because IJK won't be that IJK after some time. Cool. Yeah, great. Cool. Yes, yes. That IJK. I will make the changes and I will upload into that drive, and I will share you the link. Also, this video will be there. Where are you from, Rafael? Oh, wow, great. Hmm. So, do Russian people take NPTEL courses regularly? Oh, oh, I never knew this. Okay, I'm feeling so proud right now, like as a Indian. So that okay, great. Oh, cool. Okay, okay, I will share. Great. I think we can call it a day. It's 8 o'clock here in India. So, cool. So you can mail me, message me. Okay, I'm here. Even if you are taking vibration structure course, you can also have doubts on that, because actually I'm taking a course on that in my own institute. So actually PMRI had to like in this PhD you have to do two teaching activities, one inside institute and outside institute. This is kind of outside institute. We can have one inside institute also. So that there I am taking the vibration structures, what you're talking about, the finding the solution, coming up to the 2 degree of freedom, then finding the solution. So it's still an undergraduate course, but still I've been taking that for the past 3 years, so maybe I can help you. Okay, so let's meet up next week. Great. Bye.